Hi, I'm Jackie Sullivan, and this is my video lab report for Lab 2, the magnetic field of a bar magnet. The goal of this lab was to experimentally measure the magnetic field produced by a bar magnet and to compare that field to the predicted behavior using the law that we learned in class. I can't pronounce the name of this law, so I'm not going to try. I investigated how the magnetic field changes with a distance from the magnet, both along the axis and off to the side, to determine how that would affect the actual magnetic field. Using GlowScript, I also modeled the expected magnetic field behavior. The results were that we found N is equal to negative 2.9466, and we also found the magnetic dipole moment was 5, and I have calculations for this later. The system is the magnet, and the surroundings is the Earth. Some fundamental physics principles are the law that I mentioned on the first slide, and this defines how an electric current creates a magnetic field and defines the relationship between that magnetic field and other variables such as velocity, charge, and distance. The magnetic field of a dipole is also extremely important in this, and it shows that a magnet is a closed circulation and acts as a dipole, and basically that was also key in this lab, and the magnitude of the magnetic field of the bar magnet will decrease with increasing distance. This is also seen in the law. So unfortunately, due to some bare feet issues, I don't have pictures of my actual law because I couldn't figure out how to crop them without having my bare feet in it. But you can see the orientations that we use. So that first one would be our parallel or on axis. And then we see that we did two different orientations for the off axis to get that parallel magnetic field. I mean, not parallel, perpendicular, sorry. So this was the data for the on axis. And you can see in the graph how we linearize to figure out E and then also R and some other variables. So that's going to be key later, is using the linearized version of that law. You can also see all of my distance measurements and then what the magnetic field was at that point. Here's the calculation. So using the on-axis data, I linearized the relationship between magnetic field and distance using a logarithmic fit. And this helps me find the exponent N and calculate the magnetic dipole moment. So you can see all of my calculations here. I then repeated the entire experimental process for off-axis, and you can see all of my data that I collected for off-axis. So I also modeled this in GlowScript, and you can see all of my initial conditions in the first part of the code. So I made sure to put in all of my calculated values, including like the distance and also what we calculated mu to be. And then you can see all of the arrows that turned out. This is about what we expected and close to what we got in the experiment, obviously with some minor differences between like some of the sizes and magnitudes of the arrows. So from the observations list, we saw that the magnetometer is far away from the magnetic field. It measures near zero magnetic field in the X direction. So whenever that bar magnet is far away, and as the magnetometer moves closer to the magnet, the measured X component increases. So some sources of error is I do live in downtown Houston in an apartment. So I don't have like a yard or anywhere I can do this outside without the influence of additional magnetic fields. So basically the pull of those multiple electrical appliances, as well as just the magnetic field of the Earth, is of course going to help skew these results and is a large source of potential error for this experiment. So for the discussion questions, what if the setup was oriented at some angle with respect to Earth's magnetic field? So this would actually change the entire net magnetic field that we're getting, because we're going to have that influence of Earth's magnetic field and a lot of that pull. So that's going to basically skew our results for whenever we think we might just be isolating our bar magnet, we're actually getting some magnetic pull from the Earth. And if this experiment was repeated with two magnets stuck end to end, the direction of the magnetic field would still point in the same direction, but it would be double in magnitude since we now have two of those magnets. So that is all that I have for this. So in summary, this lab showed how well the theoretical models in the dipole field predictions align with real-world magnetic measurements. And despite some environmental noise, the data supported the relationship that we were expecting. So it was relatively close to what we would expect from that law. And I just wanted to say thanks for watching my video. And you can find a link to my glow script code in the video description if you'd like to run the model yourself or look into that a little bit more. Thanks.